So here's our first example of working with gas taken through a cycle. We're told to find in this question the difference in energy at point B compared to point A. In other words, the change in energy in going from A to B. That's what we're after. Now, if we knew the temperature of the gas at both points, there's a way to figure it out directly. Well, we don't know that in this question. We don't even know the number of moles of the gas. So we have to take a different approach. We could try to do Q plus W, use the first law. But all I know about A to B is it's adiabatic. That means Q is 0, but I don't know what this curve is. We haven't learned it yet, so we can't do an integral to figure it out. So the direct approach of finding the change in energy, we have to save for later. In this question, we got to go around, take a different strategy. We're going to go a roundabout way. Instead of A to B directly, I'll go A, D, C, B and find the changes in energy along every leg and then add them up to get the total. First, I want to change units. The graph's given in atmospheres. But if I want to calculate work in joules or kilojoules, I need to convert to kilopascals. The conversion is a factor of 101. In other words, 1 atmosphere is 101 kilopascals of pressure. Okay, so first I'll take the change in energy in going from A to D. In going A to D, I'm told that, well, let's look, it's D to A, that's the gas shrinking because it's been iced down and heat is taken out of it. To reverse from A to D, I would have to put in 371 kilojoules of energy. So the Q value is known. The amount of work that's involved, I can figure it out from the graph. Work is minus the integral of PdV. Well, in this case, since the integral just gives me a rectangle, then I know that it would just be minus P times delta V, the change in volume. Okay, so now let's plug in. Q, I'm told D to A, it's iced down, 371 removed, that'd be negative 371. But going A to D, you'd have to put 371 in, an input of 371 kilojoules as heat. Now I have to plug in the pressure. The pressure here is 101 kilopascals multiplied by the change in volume. Now remember, volume changes can be positive or negative. In this case, it's an expansion. It means the volume grows by 1 cubic meter. So I just got to multiply by 1 cubic meter. And we saw before that pressure times volume has units of joules. In this case, it's kilojoules. So it's 371 minus 101, that's positive 270 kilojoules. That's the increase in energy in going from A to D. Worth noting that heat is put in, so the gas gains energy by the heat being put in, but the gas gives up a little bit of energy by expanding outwards. And when you push outwards, you use some of your energy. And that's what's happened here. The gas used up 101 kilojoules to push outwards. Okay, now D to C. That one's easy because we're told from D to C, it is isothermal. And if the temperature of the gas doesn't change, that means the energy of the molecules isn't changing, and there's no change in energy at all. This is from D to C. And that's just given to be 0 because it's isothermal. There is Q and there is W along that. They just balance each other exactly to maintain the temperature. Then C to B is the last leg. Delta E CB. So in this case, I'm told going B to C that requires an input of energy because that's making the gas expand, you heat into it. But the other way, you have to extract 345, so negative 345 kilojoules. minus P delta V. The pressure is now the P3 value. Delta V is going to be a compression now. So this is minus 345 minus P3, which is 303 kilopascals. And now look at this change in volume. The change in volume is now a compression. The volume shrinks by 0.31 cubic meters. So delta V is negative. Negative 0.31 cubic meters. Notice how there are two minus signs, one from the definition of W and the other one from the change in the volume. That's negative 345. Heat taken out of the gas plus 94. That's energy put into the gas since it's being compressed from C to B. That's a total change in energy, which is negative 251 kilojoules. Of course, we want from A to B, which is the total along these three legs, the total change in energy all the way around from A to B comes out to be just plus 19 kilojoules. In this question, we're looking to find the amount of heat which leaves the system as it goes from C to A as part of the cycle. It's a shrinking of the gas. Heat has to leave the gas to make that happen. What we know is from A to B, we're told that the heat added is 20 joules. That's QAB. That's heat that has to be put in to pressurize the gas at a constant volume. We're told that's just 20 joules. B to C, we're told, is adiabatic. That means that QBC is equal to 0. Finally, we also know that the net work done during the cycle is 15 joules. That means we know the value of W. Now, W is not equal to 15. In fact, notice how this is what we call an engine cycle. It runs clockwise. Clockwise cycles actually give out energy from the gas overall. So in other words, the value of W is minus 15 joules. So we got to be careful about that. The net work done, the cycle is 15 joules. That's actually energy given out in the cycle. The gas loses 15 joules by work. Okay, so it's a cycle. So because of that, the change in energy is 0. In other words, Q is equal to minus W as the net effect of the cycle. This is how we'll find Q on the unknown leg, because I know the total W and I know the other two values for Q, so I can figure out the third one. So in other words, the total amount of Q, that's QCA that I'm trying to find, plus QAB, which is 20, plus QBC, which is 0. That all must equal minus W, which is plus 15. In other words, QCA must be minus 5. Does it make sense that it's negative? It's a compression of the gas. How do you make a gas shrink at a constant pressure? You ice it down and you remove 5 joules of heat. In this cycle, we're trying to figure out the amount of work done going C to D. Now, normally you'd say, oh, it's going to be a rectangle, and I'd try to do an integral, but we're not given any specific information about the pressure or the change in volume, so we can't take that approach. We have to take a different strategy. If I want to know the work done going C to D, what I'll do is compare it to the change in energy and the heats that are involved and figure it out in kind of an indirect way. So what we're told here is in going from A to C, it's the gas loses 200 joules. Now, of course, that means going C to A would have to be an increase by 200 to get you back to the same state again. So what I know is the change in energy C to A is actually plus 200 joules. Doesn't matter what path you take, it's just the change in energy. No matter which path you take, you get the same answer. Now, on the other hand, this is equal to the heat plus the work in going C to A. Okay, so I want to know the work C to D. So I'm going to take the lower part of the cycle. The Q will be QCD plus QDA plus the work CD, which I'm trying to solve for, plus the work dA. Okay, so what do I know about these things? Well, QCD is given. It's 180 joules. D to A is also given. It's an additional 80 joules. So those together combine to give 260 joules of heat to make the gas expand and then to pressurize the gas at constant volume. Both of those require putting a burner under it to warm it up. WCD I'm trying to solve for. WDA, well, there's no work. It's not expanding at all, right? So no expansion, no delta V, no work, plus 0 from that part. That is 0. That's enough to tell me that WCD, it's got to be negative 60 joules. So able to figure it out in that indirect way by looking at the heats and the work. That's the work input to the engine, to the gas, right? Negative, meaning the gas actually gives out 60 joules. The question that's asked is how much work is done on the gas as it moves from C to D, and that is negative 60. It's actually the gas is giving out 60 joules.